Hi everyone, welcome to our team Warriors. My name is Mandy and I'm going to introduce you to our hackathon project on LMI data synthesis competition. The outline is EDA, data preprocessing, autoencoder data synthesis, model building using linear regression and XGBoost. In the EDA, we show the data information and also the correlations on each two features, and also the missing rate for each feature and unique rate for each feature. In the data preprocessing, we remove unnecessary features such as POBP, which has more than 50% missing value. Second step is use the simple data imputation, and the third step is save preprocessed data to pickle file, which is easier for next step. And this is the scatter plot for numerical features after imputation. And for data synthesis, we use autoencoder. We use TensorFlow to code autoencoder to synthesize new data as well as predict salary. Our input are the data without salary features. However, unlike the normal autoencoder, our output are the data with salary features instead of sharing the same structure of input data. The idea is that we want the autoencoder neural network to figure out the relation between salary and the other features in the training process. At first, we encoded the data into 3 dimensions as the dimension reduction and visualize this 3D data to figure out if there is correlation between the data and the salary. The color of the points reflects the value of salary. The darker, the lower salary, the brighter, the higher salary. The GIF shows there is an obvious correlation between data points and the salary, but it can be explained by regular line linear relationship. In addition, the data points are located on one plane, which indicates 2 dimensions are enough to store the information of original data. So for encoder, we create 7 layers of neural network, and in the decoder, we also use 7 layers of neural network. And in the loss function, cost function, we use reduced mean, and we use item optimizer to minimize the cost function. Okay, so let's evaluate autoencoder performance. There are 2 plots, and the plot on the left is the test encoder with testing set. The color shows the value of true salary of each point, and plot on the right is test decoder with testing set. The color shows the value of a predictive value created by the autoencoder of each point, which means the dot on the left is the real value, and dot on the right is the synthesized data value. So here we can see that 2 similar plots indicate that autoencoder successfully keeps the important information based on the data distribution and also based on the color map. So we use the decoder to synthesize new data. Although we can choose a random 2-dimensional points as the input of decoder, we still hope our random sample has a similar distribution as the original data. We finally work out a way to generate samples with the same distribution of given data, randomly pick up a point from a data, choose 2 random values from a normal distribution, and add the values to each dimension of the point respectively. We assign a large variance of a normal distribution if we want a very different sample. Then in the model building, first is the linear regression. Here is a list. We find that linear regression has the best performance when we choose mean square error as the performance index. Although more complex model like random forest regression can solve the underfitting issue of linear regression, they are too complicated for data because it is overfitting and have a large MSE on test set. The residual plots are a commonly used graphical tool for diagnosing regression models. They can help detecting nonlinearity and outliers and check whether the errors are randomly distributed. So from the plot on the left, we find that the residuals are not randomly distributed and didn't scatter around the central line. central line like an oval shape, which means that our model is unable to capture some explanatory information which has leaked into the residuals. So next we use the XGBoost by H2O. H2O's AutoML can be used for automating the machine learning workflow, which includes automatic training and tuning of many models. So here we can see the code is very simple. You just need to load the train and test, and you set the number of the models you want. Here I set as 15, and after that, it will give you a list of models that which best fits for your data. So on the top one is the XGBoost. It has the lowest MSE mean residual deviance. And the output on the training in the first two plots, it shows you the model details. Like for example, it gives you the MSE in the training dataset and also in the validation dataset. It has 5-fold cross-validation as a default. And the second plot gives you a more detailed table, shows the mean SD cross-validation 1, 2, 3, 4, 5, and in each column it shows you MAE, mean residual deviance, R squared, etc. And on the third plot, you can use it as prediction. So in our test data set, we predict the result. It shows the MSE mean residual deviance. And you can also save the output, which is the prediction, as CSV file. So let's go to a quick demo and code walkthrough. So this is the GitHub that we store all the information, which is all the same as the file in the zip file. And let me explain what it looks like. So we have code file and data file and presentation and saved model and others, and you can find the file corresponding to each category. And if you want to evaluate the performance of model, there are two ways. The first is linear regression. Our model is saved in prediction model pickle. So you just need to load your data, test data in synthesis evaluation Jupyter Notebook. So here is the file, and you just need to input your file into X test and Y test, and then you can run or your outcome here. And the second choice is use XGBoost model, which is much more simpler. You just open your terminal and copy paste this line. Python pipeline predicting true data PY from demo Excel, and you can choose your data to replace the demo Excel, and then you open your terminal and just run it. Wait for a few seconds, it will give you output. So here it is the data after imputation. Give your first 5 rows like a graph look, and then you can see that there is MSE and mean residual deviance is. You can use it as the evaluation of the performance. And after that, it also do the prediction. It is saved in the test predict CSV. So you can find the test predict CSV at here after your prediction. Okay, that's all our presentation. Thank you for watching our video.